In our final module, we will explore the engineering behind the Multiscan radar and finish with recommended operating procedures. With auto selected, Multiscan uses two radar sweeps at two different tilt angles to collect the terrain and weather information in front of the aircraft. The resulting weather and ground data is digitized and stored in a temporary memory buffer. Multiscan then utilizes a terrain table that resides in the radar to determine its geographic position and initial tilt angles. The computer then uses this data to draw a conformal line above the terrain. Ground clutter is separated from weather returns by measuring the relative power from a return in each of the two beams. For instance, by measuring the power of this return in the first sweep and comparing it with the power of the return in the second sweep, it is possible to determine if the return is above or below the conformal line. All returns above the line are retained as weather. Returns below the line are rejected as ground clutter. As a result, all the weather above the conformal line is stored in the computer memory. However, in order to prevent unnecessary deviations, only the weather that is in the aircraft flight path is displayed. You'll recall from the first module that this results in a clean screen and adherence to the quiet, dark cockpit philosophy. Thus, only threat weather is displayed. The end result is a ground clutter-free display with weather from the nose of the aircraft out to 320 nautical miles. There are a number of subsystems that support the radar operation. SmartScan ensures rapid updates of the weather in turns, even though multiple scans are being used. The radar accomplishes this by performing a sector scan in the direction of the turn. Weather on the back side of the display is pasted in from computer memory. In this example, the aircraft is in a 45-degree turn, and you can see that the black wedge that indicates no information is negligible. True Zero compensates for aircraft-induced tilt errors that are invisible to the radar. Multiscan scans in front of the aircraft and compares the returns with its terrain table information. If errors are detected, a 3-axis trim correction is made and stored in the computer's memory. If a new RT is installed, the aircraft must be level and 17,000 feet above terrain as opposed to water for True Zero to engage. Note that ground clutter may be visible on the display before True Zero engages. Multiscan has several features that are designed to prevent unintended thunderstorm top penetration. One such feature that was described in detail in Module 1 is automatic temperature-based gain. You can review the details in Module 1. Remember that manual max gain and auto cal gain are very similar in appearance. While in auto, increasing gain above cal may result in unnecessary deviation. Overflight protection is yet another feature designed to prevent inadvertent thunderstorm top penetration. Details of this feature were discussed in Module 2. Finally, in Module 3, we looked at the difference in thunderstorm characteristics in different parts of the world and how the geographic correlation enables the radar to determine the inferred threat and predict cell heights. So, recommended operating techniques. We recommend that the radar be operated in auto, cal gain, and weather plus turb. However, due to the fact that the radar does not display weather below the aircraft flight path, an acceptable operating technique is, just prior to top of descent, manual may be selected and tilt adjusted to examine the aircraft descent flight path. Auto can then be re-engaged.